So good afternoon. I am Pramod Gaval, a research scholar, Department of Chemical Engineering, IIT Guwahati. So I am going to take a problem solving session two on a NPTEL course of Chemical Engineering Thermodynamics, week 2 on a second chapter application of first law. The course tutor is Professor Sashidhar Gumma, Chemical Engineering Department, IIT Tirupati. So I am a teaching assistant of this course. So I think all of you have gone through the week two lectures which was available, which are available on SWAYAM portal. So based on that concept, I am going to solve some problems and also explain some concepts. So starting from the ideal gas. So generally, there is one relation PV is equal to nRT. This is the ideal gas law. So there are some conditions to follow this law, like volume of molecules is negligible in comparison with the total volume of the gas, and intermolecular force are the negligibly small. So there are also others equation of state which follow the which applicable for the ideal gas. So AP is equal to PVT is equal to 0. This is a simple equation of state which applicable for the ideal gases. So here R is equal to gas constant, N is the number of moles, P is pressure, V volumes, and T is the temperatures. So there are number of processes involved in the ideal gases such as isothermal process, isobaric, isochoric process, adiabatic process. So starting from the isothermal process, so isothermals means temperature constants. So this relations comes after solving the first law of thermodynamics. So here, right. So here is a Q positive means heat added to the systems, and here is a negative sign means work done by the system on the surrounding. So here Q I already explained. So the sign convection here. So at isothermal process, temperature is constant. Temperature is constant means change in the internal energy depend on the temperatures. So here is the temperature is constant means del is equal to 0. So Q is equal to W. So is equal to PdV. So can integrate this and put the value P here, RT divided by V, then you get these relations. Now next process, isobaric process means constant pressure. So it's a similar way, like it relations comes from the this first law of thermodynamics. So it is a constant pressure. Really is equal to these differential forms, right. So we can write down dq is equal to Cp dt at constant pressures. This is the PdV. This is the. Now we know the relation of enthalpy H is equal to U plus PV. So differentiate it, dH is equal to du plus PdV due to the constant pressures. Right. One minute. These relations du plus PdV is equal to Cp dt, right. So this dH is equal to Cp dt, right, is equal to Q. In terms of integration, you can write down T1, T2. All of you clear?
Yes, sir.
1 minute. Now third process, isospheric process. It means constant volume. Right. So here is the first law of thermodynamics for the closed system. Du is equal to dq minus dw. So here are constant volumes, so it get cancelled. So which is equal to heat capacity at constant volume dt. Right. And in terms of, you can write down T1, T2, Cv dt. Now coming to the adiabatic process. 1 minute. So, okay. Fourth one is the adiabatic process. Adiabatic process. So here is no heat interaction between the systems, right? So dq is equal to 0. Like so it gets 0. So wait. So we are done. We can write down PdV. So we can write that du is equal to Cv dt minus PdV, right. Now based on the ideal gas, PV is equal to RT. So put the value P is equal to RT by V in this equation. Right. So dy V. Right. Now there is a one relation Cp is equal to Cv R. So we will say in next slide. Then we divide by as a Cv for the whole terms. And Cp divided by Cv is equal to gamma. Right. So we can write down R by Cv is equal to gamma minus 1. So dt by d is equal to minus gamma minus 1 is equal to d by dt. Then we have to integrate to limit by t1 to t2 here. So what's 1 minute. So ln t2 minus t1 is equal to, here a minus sign, so I can write, sorry, ln v1 divided by v2. Here is a change from earlier due to the negative signs. So I can write t2 is equal to v1 v2 gamma minus 1. All of you got clear this one? This is the relation for the adiabatic process. Okay. Okay. So for adiabatic process, we got T2 T1 is equal to V1 V2 gamma minus 1. So can I write down this form into this ones? TV gamma minus 1 is equal to constant. When put the this based on the ideal gas, so we will get some relation T2 T1 is equal to P2 as P1 is equal to gamma minus 1. So this expression got from this from above equation. So for adiabatic condition, PV is equal to P raised to the power gamma is equal to constant. Right. Yeah, here is a relations for adiabatic process PV P into V raised to the power gamma is equal to constant. Then this one relations. Then T for the TP. Then the were done calculation for adiabatic process W is equal to CV T minus T2. Then here is one relations W is equal to P1 V2 divided by gamma minus 1 into P2 divided by P1. P2 divided by P1 is a compression ratio which indicated by the R. This is indicated the compression ratio. 1 minute. This should be the W. Right. Then a polytropic process P into V raised to the power delta is equal to constant. So here is a difference value for different process. So when delta is equal to 0 for the isobaric process and infinity for the isochoric, and delta is equal to 1 for isothermal, and delta is equal to gamma adiabatic process. This is a graph in path of polytropic process characterized by specific value of delta. The P versus V is show the graph with respect to the value of the delta. Now coming to the questions. So that the Cp minus Cv is equal to R for an ideal gases. I'll have to try to solve. Are you following or not?
Yes, sir. We are following.
Okay, good. So try to solve.
Yes, sir, we are following.
So we know the enthalpy H is equal to U plus PV, right? Now differentiate it. DH is equal to DU plus DPV, right? We know the ideal gas law, PV is equal to RT. So put the PV value here. PV is equal means RT value here. Here R is a constant, that's why outside, right? Now we can write down DH is equal to Cp dt, right? And du is equal to Cv dt or dt. So heat capacity for constant process Cp dt for constant process and constant volume which is equal to dH, and for constant volume du is equal to q Cv dt, right? Now dt get cancels, so Cp minus Cv is equal to R. All of you got clear?
Yes, sir. Yes, sir.
Okay. Now coming to the question 2, here is a statement. So air enters an adiabatic compressor at 300 Kelvin. The exit temperature for a compression ratio, here is a compression ratio P2 by P1 of 3, assuming air to be the ideal gas. So here gamma is equal to Cp divided by Cv 7 by 5 and process to be reversible. So we have to solve the exit temperature, right? Here T1 given, here is a pressure ratio is given, P2 divided by P1. So I have to calculate T2. I'll have to try to solve this one. So this is based on the adiabatic process. Reversible adiabatic process. Right. So for adiabatic process, PV delta is equal to gamma is equal to constant. Right. So PV is equal to RT. This is the ideal gas. So put the value of V is equal to RT by P. Right. So here P RT by P gamma is equal to C. Right. So I can write down P minus gamma is equal to T gamma. Right. Now so here T is equal to 1 minus P 1 minus gamma, right? So T gamma is equal to, can I write down this one? T raised to the power gamma is equal to P raised to the power gamma minus 1. So is equal to 1 minute. Right. So when I bring it denominators, one minute. So we derived one relations before starting the sessions. T2 minus T1 is equal to P2 minus P1 gamma minus 1. So here I get I confuse. So UPO solves like T V gamma minus 1 is equal to constant. So from this relation get this one relation. Now put the value here. T2 is equal to T1 P2 minus P1 gamma minus 1. Sorry, gamma minus 1 divided by gamma. So here is a T is a 300 and compression ratio 3 and gamma 7 by 5 divided by 7 by 5, right? So 2 by 5 means 1 minute. मोबाइल दे तू बंद करना है इसको. Hello? 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 Here is a network issue. One minute. So all of you got this answers. T2 minus T1 is equal to P2 minus P1 gamma minus 1 gamma, right? A1. All of you got this one?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Now question 3. The pressure and temperature of an ideal gas with a constant heat capacity undergoing a reversible adiabatic process are related by. The option are here. So same adiabatic process, just we have to derive the relations starting from the first law of thermodynamics. So just we derived the T V gamma minus 1. All of you follow. Right. So put the value V is equal to RT by P in these relations. Gamma minus 1 is equal to C. So here is equal to constant. So T gamma is equal to, I can write down P gamma minus 1. So now T is equal to P gamma minus 1 gamma, right? So when we bring P to this side, right? So option A is right. All up clear this one. Here TV is equal to gamma minus 1 constants, so which comes from the first law of thermodynamics. Then put the value of V RT divided by P here. Then we choose process to solve to make it a simple one. So final got this one. Hey, everybody got clear or not?
Yes, sir.
Okay. Now coming to the question number 4. An ideal gas undergoes expansions and according to the process PV raised to the power 0.5 is equal to constant. The temperature of gas during the expansion process. Option are here does not change, increase, decrease, means the temperature of gas. See decrease, then change depending on the initial conditions. Here is the expansion going on. and PV is equal to, sorry, PV 0.5 is equal to constant, right. Generally from expansion process from state 1 to the 1 to 2, so pressure should be means final pressure will be reduced compared to the initial ones. So we solve one. So I can write down that is P1 0.5 is equal to T1 P2 0.5 into T2 0.5, right. So T2 divided by T1 is equal to P1 divided by P2. In expansion process, generally final pressure will be reduced. So means P2 less than P1 for the expansion process. So it means P1 P2 greater than 1. So what will be the final temperature? So here we got from this statements P1 is greater than P2. So means final pressure is less than the P1. So what will be the temperature? It should increase or decrease? Can someone tell?
Increase.
Yes, right. Now question 5, consider a piston cylinder arrangement containing a gas. The system is heated by placing it on the top of a burner. The system undergoes. Here is a different process given in the options. Can someone try to solve this ones? All of you understood a question or not?
Yes, sir.
Okay. So this is a gate questions, this one. Like this is a systems. By placing it on the top of the burner system. So what would be the answer? क्या सब बनते?
I think sir B is the right.
Yeah, right. A constant pressure. Generally, upon heating, the piston occupy at a higher position, and pressure remain the constant for the open system. And when heating for the closed system, means closed rigid container, the volume is a means volume is a constant. So here is a constant pressure process.
So this is a reversible or irreversible process,
Yeah.
so that the pressure remain the constant on.
Yes. Yes. Right. One. Now question 6, numericals 1. 1 mole of methane is contained in a leak-proof piston cylinder assembly at 8 bar and 1000 Kelvin. The gas undergoes a isothermal expansion to 4 bar under reversible conditions. So methane can be considered as an ideal gas under this condition. The value of universal gas constant is 8.314 kilojoule per mole Kelvin. The heat transferred in kilojoule during the process. I'll have to try to solve and tell the answer. So in this question we have to apply the first law of thermodynamics. Q minus W, or you can write down Q plus W. So work done by the system on the surrounding here work done by the surrounding on the systems. So here is the isothermal expansion. Here is the P1, T1. This is the P2, right? Are given. So for isothermal process, temperature is constant. So internal energy to depend on the temperatures. So delta, this one is a 0. So is a Q is equal to W. Hello, am I audible to all?
Yes.
Okay. Here is a light issue. Okay. So so this one is 0 at isothermal conditions. So Q is equal to W is equal to PdV, right? So you can write this one ideal gas RT by dV ln V2 by V1, right? Or RT ln P1 by P2. Put the value all given here in the statements until the answer final one.
Five 5762.8.
Right, in kilojoule, right? Right.
Joule per mole.
Kilojoules. 1 minute. One. Here is a Here is a given 1 mole of methane.
Okay.
Right. So here is the positive signs Q. So means heat added to the systems. Right. And when we follow the this one this means equation Q plus W means work done on the systems. So Q is equal to minus W, which is equal to minus PdV, right? So it should be the negative value, 5.763 kilojoules. So heat is transferred from system to the surroundings. It is the heat transfer to the systems. So which one is the right? This one, first one or second one?
One is right.
Yeah, right. Now coming to the question number 7. An ideal gas with a molar heat capacity Cp 5R divided by 2, where R is the gas constants, is compressed adiabatically from 1 bar and 300 Kelvin temperature to pressure P2 in a closed system. The final temperature after compression is 600 Kelvin and the mechanical efficiency of compression is 50%. The work required for the compression in kilojoule per mole Kelvin. Option are here given here. Try to solve and tell the answer. This is also based on the first law of thermodynamics. We have to follow the first law of thermodynamics for the closed systems. It is a adiabatic process. So Q is equal to 0, no heat interaction with the systems. So here is as work required for the compressions. So means W is a positive. Right. So we can write down for ideal gas Cp minus Cv is equal to R. So Cv is equal to Cp minus R. So 5 by 2 R minus R is equal to 3 by 2 R. Here 3 by 2 or 600 minus 300. Put the value of R here and
12.471 kilojoule per mole.
right, 12.48 kilojoule. So work required for the compressions. So means work done by the surrounding on the systems for the compression process. Right. Statement is the same with the previous questions. So here we have to calculate the final pressure. 1 minute, sorry. When 1 minute, we forget the compression efficiency. Mechanical efficiency as compression 50%. So we got the value 5 is equal to 3.74 kilojoule per mole. So since efficiency of compression is 50%, so W required is equal to 3.74 divided by 0.5, which is equal to 7.48. Right. So we forget this one's compression efficiency, means the efficiency for the compression. All of you got clear?
Yes, sir.
Okay, 1 minute.
So
Hello.
Sir, I got the D answer.
Okay, 1 minute. So after got 12.48, so here is in the statements in the question statement given the mechanical efficiency of for the compression is 50%. So this one is 12.48 divided by efficiency. Then you get 7.48 kilojoule per mole.
After dividing the efficiency, we got 6.24 answer.
7.48. 1 minute. Calcium. 1 minute. Okay. Sorry, 1 minute. W is equal to 3/2 into 8314 to 600 minus 300. So what 3.74 kilojoule per mole. Right. Now it comes C option. When we divide 3.74 by 0.5, Three point 7.48. Please recheck it. Eight three one.
Yes, sir, got it.
Okay. So statement is same as a previous one. So here, in this question we have to calculate the final pressure P2 in a bar. means adiabatic conditions. I'll have to try to solve these ones. We have to calculate the final pressure P2. So for adiabatic process, PV raised to the power gamma is equal to constants. We have to derive the equation here. T1, T2, P1 given. So we have to derive from this relation to T1 and P1 in this term. Question 2 or 3, so we derive like P2 plus P1 is equal to
Answer is D, sir.
yes, right, T2 minus T1 with gamma minus 1, right. Answer is a D. Basically in the kit generally ask question based on the this means adiabatic process, so we have to derive some relations. All of you got same one?
Yes, sir.
Okay. Now coming to the volumetric property of the pure fluids. So for the equation of state exists which related to the pressure, molar or specific volume and temperature upon any pure homogeneous fluid in equilibrium state, and the simple equation of state is a ideal gas PV is equal to nRT, which has approximately validity at low pressure and high temperatures. So when we solve other condition like means high pressure and a low, there are also other equation of states, but here is a one PVT relations. To solve the means PVT relations, so here is some equation of states which solve from any one of the three quantities PVT as a function of others two. If V is considered function of T and P, then here. So from this relation we got dV is equal to dV by dt at constant pressure dt plus dV by dP T dP. So here volume expansivity P is equal to 1 by V into dV by dt at constant pressures, and K is equal to, that's called the isothermal compressibility, minus 1 by V into dV by dP at constant temperatures. So when we put this value in this expression, then the dV by dV divided by V is equal to volume expansivity into dt minus isothermal compressibility into dP. Right, and for incompressible fluid means density is constant, so both beta and K are the 0, since V is independent of temperature and pressure for the incompressible fluid. So there is no PVT equation of state for the incompressible fluid. So PVT equation of state is valid for the compressible fluids. So based on that, so we will see some problems. The question 9, the volume expansivity. Here is a equation given, it's a relation given, beta is equal to 1 by V for an ideal gas is equal to. Option are given. Here we have to use the ideal gas law in this expressions. So PV is equal to RT. So here V is equal to RT by PV. So we can write d by dt RT by P, right, at a constant pressure. So 1 by V to R by P, right. So we can put V is equal to RT by P in this expression. So RT right. All of you got clear this ones?
Yes, sir.
Okay. 1 minute, someone join. Similarly, try to solve for isothermal compressibility, K is equal to minus 1 by V into dV by dP at constant temperature for an ideal gas is equal to. Everybody try to solve and tell the answers. Option are given.
D option.
Right, 1 by P. Now question 11, so for incompressible fluids, both the volume expansivity and isothermal compressibility are, here is the density is a constant, so answer is a 0. Right, all up clear?
Yes, sir.
Okay. Now question 12, for a liquid acetones at 20 degrees Celsius and 1 bar, the volume expansivity is equal to 1.449 into 10 to the power minus 3 per degree Celsius, and isothermal compressibility K is equal to 62 into 10 to the minus 6 per bar. The value of dP divided by dt at constant volume for acetone is. So we know the relations dv by v is equal to beta is equal to dt. So k dp. In the statement given at a constant value. So at a constant values, these terms will get 0, right? So it b is equal to dt k dp, right? Now, so here dp divided by dt dy dt at constant value. So beta is, right, put the value where beta and k.
Sir, why dv by v is equal to 0?
So here is a constant value process. Here is also dp by dt. You have to calculate these relations. Here is a mention at a constant value. Sir, here is a not in the statement not explain like constant value or isochoric process. So here based on that here is a mention. So based on that here, so value is a constant. Question the 30 similar to the 12. For liquid acetone at 20 degrees Celsius on bar, the volume expansivity same one and isothermal compressibility K is equal to 62 into 10 to minus 6 per bar. If beta and K are the constant, the pressure generated by the heating liquid acetone at a constant value. Here is the mentioned constant values from 20 degrees Celsius and 1 bar to 30 degrees Celsius. So we have to calculate the P2. Use the same relation and calculate the answer, means P2. In this statement mention the constant value, so same concepts. So here is T1 given, P1 given, T2 given, and also beta and K given.
bar.
Right. Simple one, constant values, these terms get cancelled. So B dt is equal to K dp, right? So delta P is equal to beta K dt. So P2 minus P1 is equal to all the value given here and T2 minus T1. 241 bar, right? So all of you got clear?
Yes, sir.
Okay. So in the second chapter we saw some ideal gas law. Then process involved in ideal gases like isothermals, isobaric, isochorics, adiabatic process, then polytropic process. Then we have taken some problems, means application of first law of thermodynamics. Then volumetric property of the pure fluid. This one. Okay, thank you. If you have any doubt, please ask. Yes, someone. Am I audible to all? If you don't have any doubt, can I close today's sessions?
Yes, sir.
Okay. So we will meet on next Saturday on third chapter, second law of thermodynamics. So due to the eye injury, I was not taken on Saturday of first chapter, so I was postponed and I took on the Friday. Yes, last Friday, it's yesterday. Okay, thank you all. We'll see you on next Saturday.
Sir,
Yes.
can you please suggest some textbook for the
Uh,
subject?
subject Smith and Kevin Narayan.
Okay.
To means explain the some concepts and also there is a one book. Which one? Sandler one.
Okay, sir.
Okay. Sandler and also there is a one books. In that book explain the some practical applications. So to understand the thermodynamics, you should have to clear the concepts. Means at a practical level. Sengel one, Sengel. Sengel, James Smith, Kevin Narayana, and Sandler.
Okay, sir.
Okay, thank you. Okay, thank you all.